I'm Risto Miikkulainen. I'm the CTO at Sentient, and I'm also a professor of computer science at University of Texas at Austin. That's a very good question. That's the first class in many AI courses, is to try to define the term artificial intelligence. And there are many perspectives. One is that it's the science of trying to do what humans do naturally best, doing that with machines. Another one is that it's the science of trying to do something that's intractable, address problems that are mathematically intractable to solve optimally. And I think there's some truth to both of those. But now, in the last few years, we've seen much of the machine creativity break those barriers and actually be addressing problems that humans are not very good at. And for instance, design. It seemed to be a realm where humans can only design, say, websites or engineering designs. But now we see machines do that. And that is also part of artificial intelligence. So I'd say that in general, artificial intelligence is the kind of problem solving and mechanical problem solving where something emerges that you did not program up. You did not write as a ready-made solution, but from interactions of multiple components in your in artificial intelligence systems, something else emerges that's more complex than what you programmed up. Evolutionary computation is biologically motivated machine learning. Like neural networks are motivated by what we know about the brain and nervous systems, evolutionary computation is motivated by what we know about biological evolution. But that is really just a motivation. We take some of the elements of biological evolution and formalize them and run them computationally as an algorithm. Now it turns out that we don't have to include everything and all the details in biological evolution. So we have more freedom to explore ideas that are perhaps not happening in biology but might be helpful in computationally. So evolutionary computation is a family of methods of that kind. And they are based on, almost all of them are based on population-based search. So instead of refining a single solution, as we might in deep learning or in reinforcement learning, we have an entire population of solutions that are modified together in order to cover a larger part of the search space and discover surprising and novel solutions that way. Neuroevolution is the application of evolutionary algorithms to optimizing neural networks. And for decades, we have optimized the entire neural network, including the structure and as well the weights of the neural network. And that's been useful because you can explore architectures that are not necessarily gradient descent based. So you might have activation functions and nodes that are not possible to solve using, say, backpropagation. Also recurrent neural networks, which is actually really difficult to learn with. We can apply evolution to optimize the weights and have networks that behave in partially observable environments. So that part of neuroevolution applies to architectures and domains where traditional neural network techniques and learning do not apply to. Now, a new area has also emerged, and that is combining that kind of gradient descent learning with optimization. So very large neural networks, such as current modern deep learning architectures, have become so complex that humans cannot really design optimal architectures anymore. They are complex, and we know that that complexity matters. But how do you know that this is the right kind of complexity? It's a difficult question to answer. And there we can use evolution to optimize those architectures. How many layers? How should they be connected? What kind of elements? What kind of hyperparameters? Do you have components that you repeat? All that can be controlled with evolution. And this is now a new neuroevolution approach. And it is very computationally intensive. But now we do have the computation, so it has emerged in the last few years. Well, the research covers everything from theory of optimization to applications in the real world. And that's what makes research so much fun. There's never a dull moment. You get to do advanced mathematics, and every kind of mathematics that you ever encountered can be applied in this area. Also, you learn a lot about applications. You identify many possible ways where evolution can be used to improve the current state of the art. And that includes healthcare, it includes design, it includes robotics, and it's really fun to see your system make a difference in those areas. To me personally, what really fascinates me about evolution is that there are surprises, that you are trying to solve a problem, and evolution comes up with a problem that you did not anticipate. It surprises you, and it's an elegant solution sometimes that is much better than what you had in mind. That's what you want. You want more to come out than you put in, and that happens a lot in evolution, and that's what makes it exciting. In this project where we evolved growth recipes for agriculture jointly with MIT Media Lab, we discovered that there are some biological principles that actually do not hold. The biologists in the team thought that we would have to give the plants some 6 hours of darkness every day so they can rest, presumably. But evolution kept pushing at that boundary, and eventually we let it come up with recipes that had 24 hours of sunlight, and the plants thrived. And this was a surprise. It wasn't known, but evolution discovers that if we give it a chance. So those are the useful kind of surprises that evolution does not have the same preconceived notions about what the solutions need to be. So if we are open enough to open up the search space and let evolution explore, we will find these solutions that we don't anticipate. Another example is a robotics application where we're evolving controllers for a robot arm. The goal there is to get the fingers of the arm around a target. Now, we were working on that, and we were extending it to avoiding obstacles along the way, and accidentally broke the main motor, the vertical axis of the robot. Now, it seems that you cannot get to the target that way, because if the target is far enough, you cannot turn and reach it. You have to have the main motor for that. But what happened instead, the robot learned, or evolution, the controller learned, to move the arm away from the target slowly, and then swing it back real hard, and because of inertia, the whole robot turned around its main axis, even if the motor was in op. So this is a kind of surprise that you also want to have. We've seen it many times in robotics. We have a four-legged robot where one leg is broken, and it learns to walk on 3 legs. We were not sure if that was possible. We were working on a personal satellite assistant for shuttle bay astronauts, and we only had a number of jets was not enough to actually turn it around, but it turned out that it would just make a big large circle and then stop on a dime. Solutions like that we are not even sure if they are possible, but they turn out to be possible in a simulation. So evolution interacts with the world, discovers these ways, and sometimes they surprise you. It's potentially the new deep learning, but there are many ways in which you can be the potential new deep learning. One of them is that, like deep learning was 5 years ago, evolution consists mostly of ideas that have been around for a long time, and they are now becoming of age. Now that we have enough compute, these ideas will actually work. In that sense, it can be the next deep learning, taking advantage of this compute. Evolution might need even more compute than deep learning does. And that way, it's a little bit later when it's coming of age than deep learning. For instance, if you are evolving neural network architectures, then that means that you are actually using an order of magnitude more compute, because you have an entire population, an entire evolutionary process to discover those architectures. But I think it could be the new deep learning in another sense, and that is it's the new AI. After we have developed methods that do really well in modeling what we already know in supervised training data, we want to extend AI to problems where we don't know the solutions. And that's where evolutionary discovery can play a role. So it can be the next step in AI, next step from deep learning. Let's not just model the solutions we already know, let's discover new solutions. There are several challenges. One of the challenges is actually a practical one. We need to make sure that people understand what evolution computation is capable of. So it becomes part of the toolbox for artificial intelligence practitioners and machine learning practitioners. So demonstrating, writing about it, showing what it can do and making it available to the larger research community. That's one challenge. But then there are, of course, technical challenges. One of them is to run actual big scale-up experiments, addressing very large problems. We have several techniques that can do that, deal with large search spaces, large dimensional search spaces that are deceptive. And the next step is to demonstrate that we can solve very hard, very large problems that way, scale up. But there are also techniques that are now coming out that allow us to extend it to applications. And this is interesting that once we actually taking these techniques to the real world, a whole new set of problems come up that we haven't had to deal with before because we were only in the laboratory. But now we have to deal with, for instance, uncertainty in the evaluation and uncertainty in selection. And that's something that comes from the real world, and we are now dealing with those problems, and I think that's one important direction for future work in evolutionary computation. AI is mysterious to a lot of people, I believe, currently. But there is nothing mysterious about it. I mean, it is a collection of algorithms. And we need to educate people. And that starts in universities. It starts in making tutorials and demos, not just to awe people about it, but illustrate how AI algorithms work. And then we need tools. We need tools that people can use that make it possible to apply AI to practical problems without being an AI expert. And that has worked very well with deep learning. We have tools like TensorFlow and Torch and Caffe and others that people can use relatively easily. If they have the compute, they can apply these ready-made models to data and they can already get going. Another part of democratizing AI is that we need to have tools that make it possible for people who are not AI researchers to apply those techniques to problems. They might be domain experts, but not AI experts. And having such tools has been really productive in deep learning. For instance, TensorFlow, Caffe, Torch make it possible for people to apply neural networks to many problems. We have tools like Studio ML that make it possible to run experiments systematically, collect the data and run some hyperparameter optimization, make it practical to run experiments using these tools. And we need something similar for evolution, algorithms, neuroevolution algorithms that make it possible to apply those techniques. If you have the compute, you have this tool, you can apply it to your problem. And that's absolutely crucial in democratizing. You don't have to be a developer of this technology. You can be the consumer of this technology. It's important to have different viewpoints, both the short-term viewpoints, how to apply the technology to real-world problems, and also the long-term perspective of engaging with problems that are harder to solve and take a longer time. And that has traditionally been the roles of industry research and academic research. Now, recently it has blurred a lot. There's fundamental research being done in industries, and academia is very closely connected. And I think this is the first time in my career that I have seen this kind of synergy, and it is very exciting. So it doesn't really matter whether you're doing your research in academia or in industry, you're still addressing the same problems. But most importantly, it's the merging of these perspectives of doing research that actually has bearing on the real-world problems. And that's where we see the real benefits of having both sides work together. And we go to the same conferences, publish in the same venues, and we have a lot more interaction now than we used to in just a couple of decades ago.